Yeah, so our next speaker unfortunately is sick and at home, but he will dial in as a presentation. He won't need a moment to set this up.
Alexander, can you hear us? No.
Can you hear us?
Ja. Ja, das ist immer die Frage. Ja.
Can you say something again?
Hello, can you hear me?
Yeah.
Okay. Everything set? Can I start?
Yeah, please.
Okay. So, yeah, the first talk is by Alexander Mandl on the minimal-risk training samples for QNN training for measurements. So, during this session, we don't really have questions because the talks are also presented at the poster session on Fridays. And it's 20 minutes and you probably don't see me, so please try to stay in time.
Go ahead, Alexander. Start.
Oh, okay, thank you. I'm very sorry, first of all, that I can't be there with you guys today because of health reasons. But anyway, my name is Alexander Mandl. And I'm going to present today a paper called Minimal-Risk Training Samples for Quantum Neural Network Training from Measurements. First of all, I'm going to give a quick outline of this talk. We're going to start off with some preliminaries about supervised learning on quantum computers, which is the problem that we're studying in this paper. We're going to distinguish two different scenarios, learning from output states and learning from measurements. And we're going to focus on the second scenario and present some existing requirements on minimal risk in supervised learning, which leads us to a research question that we tackle with some analytical methods that I'm going to present. And afterwards I'm going to present an experimental evaluation of our results, and I'm going to finish off with some summary and an outlook on future work. First of all, the problem that we're looking at is approximating some target transformation that is unknown, and we usually refer to it as U, using a quantum neural network. So we want to do supervised learning, so we want to use quantum states as training samples, and this is pictured here in this scenario. We have the unknown transformation, and from this unknown transformation we know some training samples that are inputs X and some outputs Y. And these inputs to this unknown transformation are quantum states usually, and the outputs could be quantum states, but they could also be measurement results or something similar, which I'm going to talk about in a second. And the goal is then to obtain some quantum circuits, the quantum neural network, that behaves the same as the target transformation on the training data. And what we're trying to do this is to train this quantum neural network by minimizing some loss function on the training data. And the assumption then is then when it behaves the same on the training data, it will also behave the same as the target transformation on all possible inputs. And the question, if that really is the case, is described as the risk. The risk here is the average loss, if we have some loss function of the QNN, on all possible inputs to the transformation. So we have here schematically shown some set of all possible quantum states, and the loss that we use during training is the evaluation of this loss or the QNN error on some finite set of quantum states that we use for training. And what we're interested in is then the risk, and the risk is the same evaluation but now performed on the possibly infinite set of all possible quantum input states to this transformation. So we are evaluating on the whole set of quantum states. In this talk, I distinguish between two different scenarios. The first one is the scenario of learning quantum output states, and the second one is the scenario of learning from measurements or learning measurements. And these are distinguished by the information that is available. In the first scenario, we have from an unknown transformation U, the information about the input quantum state and the actual output quantum state that is obtained from the transformation. In the second scenario, we don't have this exact output state, but we have the measurement outcome of this output state when measured with some observable group. So we have an expectation value, some real valued value, that we refer to as FU of x. And during training, this is also affected. So during training, we don't have, in the first scenario, we have exact quantum output state from a quantum neural network, we refer to as y hat, and we compare these quantum states to obtain a loss function. In the second scenario, we don't have the exact output of a quantum neural network, but only again the measurement result after measuring with some observable group. And we use this to obtain two different cost functions. In the first scenario, since we're actually comparing quantum states, we can use some well-known functions that do that, and for example, you could use the fidelity of these quantum states. In the second scenario, the one we're looking at more closely in the rest of the talk, we have some real valued outputs. And in this sense, you can't really compare the quantum states, but to compare the real valued output, we can use some very well-known functions. For example, here, what we use is the mean squared error. And in the first scenario, there actually is a very important result that I want to briefly mention. And this result states that entanglement in the training samples reduces the expected risk after training. And this is usually captured in some inequality like this, where we look at the expected risk after training, and this is reduced by some function dependent on R and T. And here R is the degree of entanglement, and T is the number of training samples. So this shows that increasing the degree of entanglement of the single training samples used can actually decrease the risk after training. So it proves to be, or entanglement proves to be some valuable resource when learning from output states. So this is the first scenario that I've shown before. We have in this scenario some general bounds on the risk, and also we have information about how the mathematical structure of the training data has to look like so that this minimal or the minimum bound for this risk can actually be obtained. So we know how do I have to compose my training data so I can obtain minimal risk. In the second scenario, however, we do have some bounds on the expected risk after training, but we don't have a complete description of the training data. So we don't have a complete description of the training data that I need to use to obtain this minimal risk. And this is where we want to extend with our work. We want to find, for the second scenario, requirements for the minimal risk after training when we are learning from measurements. And we want to do this for highly entangled data or for entangled data in general, but we also want to look at what happens in the case where we don't have entanglement. And this should prove as a first step to a more general, description of this problem or looking at this problem. Because in this first step, what we do is we limit ourselves to observables that are one-dimensional projectors, and then in the future we want to extend upon that to generalize. So how do we do that? How do we describe training samples for minimal risk? I'm first going to present a few tools that we use in our analytical discussion of this problem, and the first one is about the risk. Since the risk describes a function of infinitely many possible input states, we first have to reformulate this risk. And there are known results that do this reformulation, and we can do that in terms of the fidelity of a specific pair of quantum states. And if we do that, we only have to look at these specific quantum states and not the infinitely many quantum states. The second thing is the training loss itself might impact the performance of the training, so it might impact the risk. And since we want to have some general description of the risk of the training that is independent of this training loss, we use a reformulation or a guideline that is called perfect training. Here, the best case more or less is taken to investigate the performance of the QNN. So we assume that the quantum neural network can actually reproduce the training data correctly and then infer how it performs on arbitrary inputs to get some information about the risk. And the first result that we have in that regard is in the setting where we have no entanglement and we replicate some operator U when measured with some observable O. And we do this using some set of training samples. And we found here that there's actually one specific training sample here and in the rest of the talk referred to as gamma, that together with its associated output after measurement is enough to train the quantum neural network with zero risk. And this result we also investigated with entangled data. So in this case, we now want to look at training samples that are entangled with some auxiliary system and see if that influences the training process. And this entanglement with the auxiliary system means the following. Each entangled state we can show by its Schmidt decomposition. This is a formula given here. And this formula is comprised of a set of coefficients, called Schmidt coefficients, with a positive real-valued coefficients, and a set of basis states which are orthonormal and form the so-called Schmidt basis states. And we found that if the training input X, this training input contains the training input gamma that we had on the slide before, as some Schmidt basis state with the largest coefficient in the front here, Ci, then this entangled input suffices to train the quantum neural network with zero risk. So as an example, an entangled state could look like this, where we have one term that contains this training sample gamma, and C2, its coefficient, is the largest Schmidt coefficient in this whole set of training samples. Just as a small note, this always holds if Ci squared is greater than 1/2, since this training sample decomposition is actually normalized. So we found with analytical method some specific training samples that minimize the risk, but we don't have an idea how entanglement in general affects it if you don't have specific training samples. So for example, we found that entangled training samples still work, but using entangled training samples actually makes the composition of the training samples more complicated, because now we actually have to look at the Schmidt coefficient of these training samples and not only the training samples themselves. So what we do in our experimental evaluation, we want to first of all evaluate these analytical findings, but also investigate the performance if you don't have this full control of the training data. If we can't make sure that this training sample gamma is actually part of the set of training samples. So here we use random inputs. And our experiments are performed on a simulator using the following setup. And we first randomly sample some 4-qubit quantum state O to obtain an observable. We build this observable as the projector. Then we randomly sample the 4-qubit target operator U. We use this as the target operator that is supposed to be learned in our experiments. And we generate the training data according to the results that we want to investigate. More on that in the next few slides. And we optimize some quantum neural network by minimizing its training cost. And here we use parameterized quantum circuits as the quantum neural networks. And then, after we've trained this quantum neural network, we calculate the risk after training to get our results. And the first experiment I want to present looks at the influence of the Schmidt coefficient Ci in the training sample, in the entangled training sample. So if I have the training sample gamma, but I don't have full control over the Schmidt coefficient, how does this affect my results? So we plot here, for training with one training sample, the coefficient, we vary the coefficient of this gamma in the entangled training sample and train quantum neural networks and calculate the average risk after training our quantum neural networks. And we compare this to a baseline, and the baseline is the expected risk if we don't train the quantum neural network. So if you just use a random quantum circuit, how good would it behave? And this gives us the baseline here. And the following plots show the results of our experiments for different degrees of entanglement. So this R here is the degree of entanglement. And I want to focus on the top case for R equals 2. And as you can see here in the beginning, for low coefficients, it stays near to the baseline, but at some point a very steep drop happens, and then afterwards it actually obtains zero risk after training. And this point specifically is the point I talked about before, which is the point where the coefficient matches, the coefficient squared matches 1/2, and afterwards, or for the higher coefficients, you can see that the training here actually obtains zero risk. But this plot also shows that in the left part, we actually are very close to the baseline, so we can't really give any indication how the training performs in this case, if the Schmidt coefficient is not the largest. The second example then looks at the effect of entanglement for randomly generated training samples. So here we generate training samples that are completely random, so they don't have to contain this one training sample gamma that I talked about before. And we also look at here on the x-axis at the number of training samples to see if this actually influences the performance if we increase the training samples. The baseline and the scale are the same, and the results that we found in our experiments are as follows. And here you can see that for the highest degree of entanglement, 16, the average risk that is obtained is actually the lowest. However, compared to the plot before, where we actually reached zero risk, we here nowhere approach zero risk, even after using a lot of training samples for the small example that we actually used in the experiments. But there seems to be some indication that increasing the number of training samples reduces the average risk. So what we found, to summarize, was that for these one-dimensional projectors, in the scenario where we use the measurement result of an observable to train, we found there is one specific training sample that is enough to train the quantum neural network for zero risk. If this training sample is known, however, introducing entanglement doesn't really produce a benefit. It also, the only thing it does is, if entanglement is introduced, we have to take care of which specific Schmidt coefficients we actually have in our quantum input state. But we found some minimal improvement for random inputs. However, compared to the improvements if we just knew or used this training sample gamma here, they were not as big. And we want to expand on these results in future work. First of all, by generalizing these findings to other observables, we now have some specific or very limited set of observables, which are these one-dimensional projectors, and we want to extend our results to all possible observables and possibly to all possible observables. Second, we want to look at the effect of the measurement process on the auxiliary system, because what we did right now was we used a very specific measurement process on this auxiliary system, and maybe changing this measurement process actually influences the results. And lastly, we had one assumption, which was the assumption of perfect training. However, it might be that the complexity of the training process is influenced by the exact training samples that we actually use. So we want to evaluate the cost function landscape during training to get some idea how we, or if there is some kind of influence like this that makes the training harder or easier in these cases. And with that, I want to say thank you and have a very nice few days left in Crete.
Thank you. Thank you, Alexander.
Thank you very much.
Thank you.
Since we do not have questions, we will move on immediately to the next talk.
Sure.
By Jalila.